Alright, another draft physics video presentation. Probably have to do a couple of videos today, but see how it goes. I'll try to stick to one subject in this video. So anyway, gravity. Sabine Hossenfelder. Give her some credit for recognizing that some of this modern physics is unproven, and they're talking past their evidence, and there's a lot of good reason to doubt the authenticity of many of these statistical or mathematical style experiments based on a engineered bias. And so she's got some credibility for recognizing that, but it seems that she's pointing fingers just at others doing other things than the crap she does accept as fact. Is just as suspect. I would argue that all of it, since Einstein, is suspect, and that it all needs to be held to a higher standard. So here she is defending the loop-de-doo of gravity. Now, this isn't how they teach gravity. Susskind, the authority on gravitational subjects, black holes and whatnot, teaches mock gravity. Okay, in his highest level physics course, he's not bothering with this notion that there's no force. He defines it as an anti-convergence, so he's trying to get away from the pull idea, by naming pull anti-convergence, anti-divergence. Sorry, it's just such a bizarre double negative kind of thing to do, to just basically say that gravity's just from the outside in. And it's just a pressure, and you could think of it as a fluid, and that's how he teaches it, as if it were a fluid. So anyway, so all this is academic crap. Doesn't really have anything to do with how they acknowledge it exists. And again, they basically teach, when they're just talking about gravity itself, they're teaching mock gravity. So this is all sort of bullshit.
Hi everybody. I was sick last week and I lost like 10 pounds in 3 days, which brings up the question, what is weight? Weight is actually the force that acts on your body due to the pull of gravity. Now,
so what really ought to be stated is that there's a reason why stuff moves, and weight is movement. You're just moving, okay? A bullet has weight when it hits. It weighs based on per square inch of the surface or square millimeter of the surface. There's a pressure created, and it's essentially weight. So everything that weighs something is weighing something because it's moving. Whether it looks like it or not, that's what it's doing. So its nuclear bits, the littlest, tiniest parts of it, are the thing that has the weight. And we've identified that as atomic weight. Okay, so your weight is going to be based, if you're going to measure your weight based on how something moves you, and that's how you measure your weight, you're measuring really how fast or how well your bits are being pushed, your electrons and protons. And that's the bottom line. Something has to move for there to be weight, and the thing that's moved is your mass, and your mass is made up of electrons and protons. Yes, neutrons, but they're not really. Okay, they're not really neutral. Anyway.
gravitational force depends on the mass of the object that is generating the force.
So so she's just saying it just depends on how many little bits you got, because the little bits are going to do the moving. And the little bits are the things that are interpreting the force. They're the things getting hit by it. So if the little bits are a standard size, then you can just kind of understand that a standard size thing, or like if I made a bucket, to catch rain, okay, a standard size thing is going to catch so much rain. So if the rain is a certain amount of rain that's coming down, it's going to catch a certain amount of energy, and it's going to have a certain amount of weight. And each electron, each proton is a standard bucket, and they're the thing that's doing the moving, that's creating the thing called weight. You don't have any without the electrons and protons collecting, rain, collecting a force, collecting the stuff. And all the real argument is that if you're not moving, it just means that the bucket going this way is catching just as much as the bucket going that way, and therefore you don't go anywhere. I guess I should click on this. So another point I thought worth another analogy that's similar to this bucket analogy is one you could understand if I did have a field of random force, coming from all directions. That means it's going in all directions. It's going this way, but obviously if I'm a little thing here, I'm not going to see that. I'm not going to see this going that way. I'm only going to interact with stuff heading right for me. So a random field becomes a directed field in the sense that anything in the random field is only going to be hit by things that were heading right for it. So you can get that idea of pressure. And if I was to put something in there, in that field, that was shaped, okay, and there was a consequence to the shape. So let's just say these little things, these little arrows, let's think of them as fish even. Well, the idea would be is that fish that came in this way and hit it would lose their momentum because they slide in here, they get stuck, and they just stop swimming, right? So you could say that all of their energy will be absorbed by this mechanism. So all of their energy, let's just give it a shape, so there's no doubt that it's a solid thing that collects fish. So it's trapping. All the fish that come in this way all stop swimming. They all give up all their energy. But you could sort of understand the fish coming in this way could slide across this surface and still have, they might have been going 50 miles an hour here and they're only going 20 here. So they gave up only 30 miles an hour, where so all the fish here going 50 miles an hour, they give up all 50 miles an hour. Now this is a larger surface and different things, but the fact is that if you could make such a circumstance, this simple device in the random field wouldn't just sit there like the pressure was even. It would be essentially a trap in one direction, okay, and a sieve in the other direction. The stuff goes through one way, but it can't go through the other way. So it's sort of transparent one way, a little bit transparent one way, and opaque the other way. So it would, in fact, even though the field is random, it would start going this way. And just a fact, if we can engineer such a device, this is, under these circumstances, the defined circumstances, that's what we would see it do. So even though the field is random, the device isn't going to act randomly. It's going to filter the environment and behave different. Now, the argument I'm making is electrons and protons are effectively those kinds of filters. It's a different kind of filter, but they're traps.
In this case, planet Earth. So you can lose weight by simply moving to the moon. Technically, therefore, I should have said I lost mass, not weight. Why do...
Right. So and even more technically, you should have said you gave away, you cut off some number of electrons and protons. That's what the atoms are made of. Those are the things you lost. So you lost the buckets. You lost some buckets. And so now you can't catch as much of a force. If a force is coming by, you can't catch as much of it because you don't have the same number of buckets. Simple answer.
we normally not make this distinction? That's because in practice it doesn't matter. Mass is just a number, a scalar, as physicists say, but weight, since it is a force, has a direction.
So, I mean, weight is not a force. So, so she just said to be more specific, to be more accurate, to be all this stuff. Weight is not a force. Okay, weight is a consequence of something acting on you, a force being absorbed, okay, like the bullet absorbs a force in a direction, and it gains weight in that direction, okay, because the pieces of it, the mass of it, the little bits of it, are now moving in a direction. They have individual weight, and they're moving fast, a lot faster than they were before, and so their velocity equals their momentum, and that equals their weight. Their weight is a measure of their momentum, period. That's the most accurate way to state it.
So if you wanted to be very annoying, I mean very accurate, then
Yeah. Well, you just weren't very accurate. You were incredibly inaccurate. Weight is not a force. Weight doesn't act on something. Its mass acts on it. Its momentum acts on it.
and whenever you'd refer to weight, you'd have to say which direction you're talking about. The weight in east direction, the weight in north direction. Why doesn't
So this is more nonsense. Again, weight is just recognizing the fact that you have more mass in one direction than you have in another direction, meaning your bits are in fact moving. Your electrons and protons have to move. That's where you acquire weight. And so you could argue that an electric conductor that has electrons moving in a direction has more weight in that direction. It has more mass in that direction. If you could measure it, you'd find it.
anyone ever mention this? We don't usually mention a direction when we talk about weight because
What you don't usually do is talk about gravity in the context of what it is, a nuclear force. It has absolutely no effect on atoms. It has no effect on molecules, compounds. It has no effect on objects. It has an effect on the electrons and the protons. They're the thing being moved by gravity.
we all agree that we mean the force pulling down. And since we all know what we're talking about, we treat
Yes, we all play this stupid game of playing a game where, first off, the word pull as a physics term should be kind of laughed at and ludicrous because there isn't any such thing. We know that in the real world, every mechanical pull is really a mechanical push. Friction, everything. And we can all understand that it's always, always, always something pushing on something else. Nothing ever pulls on it.
weight as if it was a scalar omitting the direction. Moreover, the gravitational attraction downwards is pretty much the same everywhere on our planet, which means it is unnecessary to distinguish between weight and mass in everyday life.
So again, there is a huge reason to distinguish between the thing that gives you the capacity to absorb rain, to collect the rain, and how fast the bucket's moving because of how much weight it's gained, how much it's collected, how much rain it's collected. So, and again, that's all that's really at issue here. So again, they always use these words as if there's no force when what they're talking about is the net effect on you. So you're going to have a net effect. You're going to be sitting here and stuff, okay, is going to be hitting you. Maybe you'll get more stuff from one direction than you get the other direction. That means the net force is only one of these arrows, but we know the real force that affected you was 3 arrows. It's always about this net. All right, and they know this stuff too because they know that gravity works this way. So when they say there's no charge inside a sphere, or when they say there's no gravity, so I did this just yesterday, but I mean I could make a hollow sphere, okay, with a skin that was say 10 miles thick, and it'd be impossible to construct just because I need incredibly strong interior structure here. But anyway, let's just say I had such a structure. I could make this without it collapsing. The point is they know, okay, they'll admit that if an object is here, there's no gravitational effect. It won't move in any direction. It'll appear to be weightless. Okay, but the fact is that it's being acted on by plenty of force. There's force hitting it from this direction, or however you want to look at it. Whether it's pull or push. Again, I just argue you should get that the default should be a conversation about push, because we know pushes happen. Pushes are the simple thing. A thing bangs into another thing and pushes it. That is, without a doubt, something that's real in physics. The idea that something crashes into something and it goes this way, that's not a very real idea. That we don't see anywhere. But anyway, so the simple point would be is there's plenty of force acting on this. It's just that we know that the force pulling it this way is, if we're going to call it a pull, is balanced by the amount of pull, okay, that's more density of pull going in all these directions. It's weaker. This is a strong force, this is a weak force, but there's more of this and a lot less of this, and therefore the two always balance. And no matter where I put this in here, it's weightless. It has no weight. There appears to be no force. But we know there's plenty of force acting on it. It's just that the net product, okay, is zero. But, just write the word net. So you know, why pretend that we're saying there's no force when we know there's plenty of force? And all you're really talking about is what's the net between the two forces acting on you. One pushing up, for example, and one pushing down. And if you understand gravity that way, that gravity really is that, if this is what's really happening, is that there's an amount of momentum, force, moving in one direction and an amount moving in the other direction, and the net is, okay, a certain amount of force, 10 meters per second imbalance on the surface of the Earth. But there's more force acting. It's just that's the net.
Technically, it's correct. Mass and weight are not the same thing. Practically, the difference.
Okay, weight is just measuring the velocity of the mass. That's all it's doing. You're just measuring the momentum, the net momentum. When you add up all the stuff moving inside of you, what's its net movement? That's weight.
It doesn't matter. But wait, didn't Einstein say that gravity is not a force to begin with?
Well, Einstein was full of shit, and the fact that you people haven't figured out that he was full of shit sometimes. I mean, look, he's a smart guy. He figured out a lot of stuff, did some good stuff, but this was a little bit of a silly theory. So he did a bunch of this stuff in his youth, a useful indiscretion. Some of the objects he was thinking about, like thinking about the vibration, Brownian motion of pollen, and comparing that to electrons, very good stuff. But some of it just a little bit too wacky, a little bit, over the rainbow. And you people should have been clever enough to figure out, well, yeah, he was just talking about his ass with that kind of crap, because it's a non-answer to the question. It doesn't explain what gravity is, doesn't explain anything about it. All it does is convert something we already know exists into, a two-dimensional fake drawing of some sort of notion of a bent thing. Then you can't bend anything in 3 dimensions, so why are we talking about it?
Ah, yeah, there's that. Einstein's theory of general relativity tells us that the effect we call gravity is different from normal forces.
So again, it doesn't have to be different. Again, when they teach it, they don't teach it in any other way than what is mechanically sensible, and that is it's a real force. It's real movement of real objects. And the objects move because there's a net imbalance in the forces acting on them. Fact. It's the only sensible way to understand it. That's why they teach it that way.
In general relativity, space and time are not flat like a sheet of paper, but curved, like the often named rubber.
Right, so it doesn't really mean anything. You're showing me your 4-dimensional space in 2 dimensions. So you're just totally copping out from your obligation, which is to make this rational in 3 dimensions. So in 3 dimensions, Susskind will admit all you have, okay, when you do this, when you do bent space in 3 dimensions, what do you have? You have a light bulb in reverse. That's what gravity is. Gravity is a light bulb in reverse. That's how it's taught. Okay, it's radiation. Okay, negative radiation, if you want to call it that, anti-radiation, which means the arrows are pointing in. Okay, and every object has this anti-radiation coming in 3 dimensions, and it's an anti-divergence. Anti-divergence means it's diverted out here and it's getting closer in here. Just means it's as it goes from out here to in here, it converges into a point. Okay, it comes from out here and it converges into a point. All right, and that's all it is. That's all it's taught as. That's what it means in 3 dimensions. There's no frickin' fabric in 3 dimensions. It's just nonsense. The real subject is there's stuff. There's a force that gets stronger as you get closer, and it's basically saying you go in. And you can have 2 reasons why it goes in. You can say pull. It's pulled. Even though there's no way for this object to grab this object and pull it in. Or you can do the simple and logical thing and say, there must be an active force constantly pushing on every little particle in the universe. Yes, right answer. The real universe is the tiny universe. That's the only universe. And in that universe, the empty space is full of little bits of crap, okay? And they're all going in random directions. And from every single point in that space, if you didn't have such things as electrons and protons, you just had all one kind of thing. From every point in that space, it looks like the universe is heading right for me. There is weight, the weight of the force, the weight of the little bits flying through space. The weight of that force will always look like it's heading right for me, and that I'm being pushed into a smaller container constantly by the universe. And it's doing it to the tiniest bit, and then when you put 2 or 3 of those little bits together, it's doing it to the collection of bits, and then when you make a human being out of it, it's doing it to the whole fucking human being. That's the rational theory. That's the only theory. Again, it's the way they teach Einstein's bullshit is taught like a reverse light bulb. It's not taught as any bent frickin' fabric. Because a bent fabric isn't 3-dimensional space. It's a complete lie. You can't illustrate the 3-dimensional universe realistically and accurately by pretending it just exists in 2 dimensions. And especially when you're going to claim there's a 4th dimension called time, which is just more nonsense.
This curvature is caused by all types of mass and energy, and the motion of mass and energy is in return.
So again, mass and energy. Energy is what's causing it. Energy is what's in the field. Energy is what's in the universe. That's what the photons are. That's what the magnetic field is. That's what the gravitational field is stuff pushing on objects and pushing not only them into a smaller space like the electron, but pushing the atom, pushing the compounds, pushing the molecules, pushing every single thing. The pressure is clearly external. There is not a negative pressure inside of things. There is a positive pressure outside of things.
Unaffected by the curvature. This gives you a self-consistent closed set of equations known...
Right, it gives you equations, but it doesn't give you any logic. And again, a closed set of equations, meaning I'm not even going to consider the existence of the force. I'm just going to, because that takes energy, I'm going to pretend that the things move, but no energy acted on them. Nothing energetic had to happen. It's just some sort of magical place where all these arrows come from. Magic made them. That's their explanation. Just like their virtual photon for magnetism, they have no way to account for where the energy comes from. The Earth doesn't burn any energy to move towards the sun, and the sun doesn't lose any energy to pull the Earth in. So they know it's not coming from the inside out. It has to be coming from the outside in. Oh, I mean, the logic is so clear.
As Einstein's field equations. In Einstein's theory, then, there is no force acting on masses. The masses are just navigating the curved space-time.
So again, the curved space-time is just the inverse square law. The curved space-time is doing the same thing a light bulb is doing. Do you have any reason to think that photons are curved space-time? Do you really think it's doing exactly the opposite, right? I mean, it's momentum coming at me, not momentum drawing me in. So it's just the opposite of. But do you really think it would make any sense for me to say, let's just forget about thinking that it's radiation hitting me. No, it's I'm obeying the bent curved space-time that's created because the light bulb went on. All of a sudden, I become a vacuum cleaner. I mean, it's just such silly nonsense. It doesn't change anything. That curvature is exactly Newton's curvature. It's exactly the inverse square law. And the inverse square law is created by a radial force, a force coming equally in or a force going equally out in straight lines will automatically, a spherical object will automatically create the inverse square law. Do it all by itself. It's a real explanation for the existence of the law.
We cannot see the curvature directly. We can only see its effects. And those effects are what we call gravity.
So again, what you should be calling gravity is something that, well, look, even the anti-divergence makes sense, right? I mean, the lines are further apart. The further away you go, the further apart they get. And the closer the lines get as you get towards the center. So if I drew the actual lines, you would know that this object would end up looking bigger and bigger and bigger because the lines would be so dense and, towards the center that you couldn't even see the object because the lines would be obscuring them because there'd be so many of the lines colliding with each other. That's the inverse square law. It's just made out of something understood as a straight line force. A straight line force does it. So why talk in this nonsense? The magical nothing moves the objects. The nothing space tells them where to go. No, something is telling them where to go. Just like the frickin' light bulb when it's on is shooting crap at me. All right, and it's real crap. It's real stuff that travels real space, and they know this gravitational thing moves the same damn speed as that light. So why are they playing this game? Like we can't figure it out. We have to settle for this stupid answer when the rational answer is right in front of us.
Now, Einstein's theory of general relativity rests on the equivalence principle.
Right, a principle he's never even messed with. You say they're not calling it a law, right? Because they don't have the guts to. Because it's just a wrong-headed. So this idea that every way you acquire weight is the same, we know in reality it's not the same. We know being pushed by, like the bullet example, I could slowly push a bullet, right? I can move it slowly and get it up to speed, right? I could keep hitting it with a force, and I could make it go faster and faster and faster. Or I could have an explosion, all right, and then create force the energy into it very quickly, which I know is going to make the bullet really hot because it's going to resist the change. You got to move all of those electrons and protons, and it's going to get kind of incoherent. Some of them are going to be going this way, and they're going to be all kinds of pressure is going to be building up, and the bullet's going to deform and do all kinds of things because of how fast I'm forcing it. I'm pushing the force in faster than the physical structure can stay maintained. Or I could slowly push it up to speed and it won't get hot and it won't deform and it won't do any of these hostile things and pieces of it won't fly off. It'll stay intact. So it's just like the space shuttle. If I want to shoot the space shuttle, I can shoot it with rockets, but I could have like a super rocket, right? A nuclear bomb underneath it. What's going to happen? Well, yeah, I'm going to try to force it a little too fast and it's going to dematerialize. It's going to break into little stinking pieces. So it's not always the same how you put energy into something. And when we're sitting here in gravity, we're getting hit by a very light rain. It's a very dense, very tiny little particles hitting just our electrons and protons individually. So it's moving everything on the nuclear scale. But if I push you with a bomb or something, I end up pushing, the pressure ends up first being interacted with all of these pieces, get very, very active, and so active that pieces fly off and all kinds of destruction happens. So clearly not all ways that you interact with a force are the same. Right now, if I'm sitting on my ass, so my ass is taking all the pressure, but if I'm walking on my feet take all of the pressure. The force isn't always the same in terms of how quickly it can get into your body. It gets into your body really quickly with gravity. It gets into your body really slowly when it has to work up first through your feet and then into your leg bones and then all the way up through your bullshit. They're not. It's not the same. There's no point in saying it's always equivalent. It's not equivalent. Gravity isn't an elevator.
The equivalence principle says that locally the effects of gravity are the same as the effects of acceleration in flat space. Locally here roughly means nearby, and acceleration in flat space is described by Einstein's theory of special relativity. So with the equivalence principle you can generalize special relativity to general relativity. Special
And they're really saying two different things, but whatever. Look, the simple point is velocity is the thing that affects time. So the faster you're going, the truth is that you physically change. That's why clocks physically change when you move them, because you're moving them through a field of force. So you're imbalancing a force. But the truth is, if you know how much rain is already falling, you can't make the rain that's already falling not fall. So this is probably a good way to understand it. There's ways to make it possible for you to move that are fundamentally different, right? So let's understand. So we have rain coming from both directions in the universe, right? The absolute universe. If I had a dead universe with just one object in it, you could understand that the rain is coming the same way from both ways. Now there's two things I can do, right? I can make more rain to move you, to change your net balance, right? This is the nets thing again. It's really important. To change your net balance, I can add energy. Well, that's going to mean that's going to be, in some sense, obviously kind of a hostile thing, because now, I'm overcoming this force by adding more force, so there's more forces acting on me. I'm still getting hit by this rain, and I'm getting hit by this rain, and now I'm getting hit by even more stuff. So in a sense, that's got to make me hotter. It's got to create the imbalance is being created in a hostile way, a positive way, you could argue. Now the other way I can make you move is that I could put something else in the field here, and he absorbs some of this. And so now I'm being hit by a lot less rain from this way. Now that's a lot less of a hostile way to get moved. I'm going to get cold, okay, not hot, because I'm not getting jiggled more. I'm not getting bombarded with more energy. I'm getting bombarded by less, okay? And I have a net in a direction, okay, that's just dictated by how wet I'm getting, essentially. And I can get less and less wet if I put more and more things in here to block forces. But I can't undo the force. I can't remove it. All I can do is block it or add to it. And technically adding to it means you had to subtract from some other force. So in a sense, you can block it by making force go one way, okay, like diverting force that was going this way into force going this way. I can add. But obviously when I did that diversion, whatever's sitting over here is going to say, hey, there's a net imbalance over here. So you have to always conserve. But again, it's just kind of just wrong-headed, in my opinion, to argue that it's the same thing for you when you have a net change that's lower than the net universe force, a lower pressure that's making you move, or there's a higher pressure making you move. Those two events won't be equivalent.
Relativity is the special case in which space-time is flat and there is no gravity. The equivalence principle was well illustrated by Einstein himself. He said, let us consider you are in an elevator that is being pulled up at constant acceleration. There's one force acting on you, which is the floor.
Right, no, but we know what's causing the force on the floor, okay? It's the fact that you're applying an uneven force. Either you put a rocket underneath the elevator or you're pulling it by some sort of rocket, okay? So it's a rocket any way you look at it. And there's the force you're applying. You're forcing a net imbalance in a direction. And obviously, from the perspective of the thing, it can't tell the difference between pushing on my feet or pulling on my head. Yes, I'm not going to be able to tell when the force is actually doing it to my elemental bits. I can't tell whether my electrons are being pulled or whether they're being pushed.
Pushing up. Now, Einstein says gravity has the very same effect without something pulling up the elevator.
Right. Well, yes, because gravity is affecting me, not the elevator. Gravity is being pushed through me, okay, and causing me to push down on the non-moving elevator. I mean, this is just so stupid. Yes, of course. Gravity's a force, just like the force you used, the machinery you had to use to move the elevator. You just changed the machinery. Now the machinery is pushing you down in the form of gravity. You didn't have any gravity with your fake little elevator. Now you have gravity. So you're just changing where the flame is. The flame was under the elevator, and now you're putting the flame on top of my head, essentially, by having the imbalance be created by the gravity.
And again, there's only one force acting on you, which is the floor pushing up. If there was nothing
So again, this idiotic notion that there's only one force acting on you, and clearly we know there's going to be two forces involved because you're going to get pushed. You are accelerating. Even when you're sitting there, I'm accelerating quite obviously because I'm denting the chair. It's just a fact. Or I'm denting my ass. And that's a fact. And that didn't happen for no reason. It happened because the little bits are, in fact, still moving. Some are going up and some are going down. And there's a net balance between the two forces as I sit here. That's why I don't move. But there's still forces. There's still, just like in the center of the earth when there's zero gravity, there's still forces acting on it. The stuff is still moving.
in the elevator, so if there was no acceleration, you would feel no force at all. In general relativity, this corresponds to freely falling in a gravitational field. That's the key.
Right. And you don't notice free falling because, again, gravity is moving your electrons and protons. It's a nuclear force. But if I replaced gravity with a steel thing or a bullet, all of a sudden you'd feel it. If I put all the force of the gravity that spreads all over your body, goes through you, if I put all the mist, the rain, into one little clump, and then I poked it in your frickin' eye, okay, you wouldn't say, free falling is benign, I don't feel a thing. You'd, of course, feel it then. It's the way the force is implemented that decides whether you feel it or not. Again, if I just pointed the floor below me, if I made the floor below me into a tiny little point, a giant arrow, and I'm sitting on the little tiny point of that arrow, I'm not going to say sitting on Earth is benign, because I'm going to be pushed right into that point. That point is going to penetrate me and, rip me a new one. And it's not going to be a pleasant experience at all. So again, this is all just circumstantial. There is no rule of equivalency. I will be affected quite differently if all you have to do is manifest the force into a different form. If I spread the force out, it's more acceptable. If I can make the force into a concise one little bit, like a gamma ray or something, then it's more dangerous.
Point of Einstein's insight. If you freely fall, there's no force acting on you.
I mean, it's just obviously stupid. Okay, clearly you are the one being affected by gravity. There's the imbalance between your butt and your head. There's an imbalance in the field, and every one of those little atoms inside of you are full of electrons and protons, and every one of them is saying there's more pressure going down than there is pressure going up. So you fall.
And in that, Einstein and Newton differ. Newton would say if you jump off a roof, the force of gravity is pulling you down.
No, he wouldn't say that because he didn't. I do not posit, speculation on a cause or however he said it. He wouldn't tell you. He didn't know. Push, pull. I don't know. That was his answer. So let's not pretend Newton said something for which he didn't have evidence, unlike you people.
Einstein says, nope, if you jump off a roof, you take away the force that was pushing you up.
So again, obviously, yes, that's why there's an imbalance. You took away a portion of the force that's keeping you from moving. But the force of gravity was affecting you when you're on the roof. It's affecting you when you're on the ground. It's affecting you in the sky. And it's affecting you proportional to how far away you are from it. Just like the light bulb, certain number of photons hit me, depending on how close I am to it. And it's exactly the same mechanism. So it's no big surprise. You take away the opposite force that's holding you. The opposite force is the earth pushing me up. It's a fact. The ground is under pressure. It's pushing this way. All right? And I can't penetrate it without increasing the amount of pressure. So it pushes me back. The electrons down there are already more compact than the electrons here. And they're just not going to accept my loose electrons invading those tight electrons.
Again, however, the distinction between the two cases is rather technical and one we do not have to bother with in daily life.
Well, you don't bother with being, again, explicit about things. So again, she called weight a force, which is just nonsense. It's a measurement of force. But anyway.
That is because
in a direction.
In daily life, we do not need to use the full-blown apparatus of general relativity. Newton's
Right, we don't need any of this nonsense. As a practical matter, it doesn't have much practical reality. And the only reason why you believe this nonsense is somehow you believe that photons are twice as affected by gravity, even though you have no good experimental evidence demonstrating it. The other woo part of it is this whole time dilation and the precession of Mercury, which you could argue is just the precession of the interior of the sun, which is moving. The inside of the sun's moving for a reason. The inside of the earth is moving for a reason. And the reason is gravity. The reason is the force. For there to be a net imbalance in the force, something has to absorb the force. Something has to divert the force or do something to the force to cause it not to get to me. The fact is the earth below me is absorbing motion in the upward direction. And that is what's making me fall down. The sky is always producing the same amount of force coming down. The force that's being changed is the force underneath me. The earth is absorbing motion. And by absorbing motion, you're absorbing the rain. You're stopping the fish. You're trapping them. Eesh.
Theory works just fine for all practical purposes, unless possibly you plan to visit a black hole. Thanks for
So more nonsense. Visit one of our figments of our imagination that we've never really proven any such thing exists, especially in the context of singularities and all this other mush, and it's all this divide by zero nonsense and infinities and silly shit. And they take no account how it is so abstract and so disconnected from a mechanical universe. This bent nothing makes stuff move. No, they've completely broken the links between cause and effect. And why somebody who'd call themselves a scientist or a thinker or an intelligent person, why they would think it's rational to accept a marginally evidence theory, a very weakly evidence theory, I would argue, that breaks cause and effect. I can only think that you're really just religious people. I mean, only a religiously natured person could think there's some reason to think you escape cause and effect. There's causes. Things move for a reason. They don't move because some bent nothing told them to do it. Ugh, this is so bad.
watching. See you next week.
Ugh. Not too enthusiastic, frankly. Yeah. What kind of horse shit will you trivially attempt to defend with, verbiage and semantics that's just convoluted? Weight is a force. No, it isn't. All right, anyway. Okay, till the next time. Yeah, we'll just leave it at the gravity subject. I don't think there's anything more to say on it. Again, I would argue, okay, there's always more to say, that the real deal is charge. Charge is the real event in the universe. The fact that electrons and protons act inversely. Okay, so if I have an electron and I have a proton, the two of them are acting inversely to each other. So I put them in the same conditions, they act completely different. And the simple explanation for that is that there's two forces. Okay, and when a blue force hits a white force, the blue is deflected. When a white force hits a white object, it's reflected. All right, and by having those two, that simple mechanism enables you to have the relationship between different charges attracting. Obviously, the same charges would end up repelling, because you would end up with a perpetual reflection between similar charges, where you would end up with all the white energy deflecting out of the blue objects and all of the blue energy deflecting out of the white objects, and therefore you would end up with low pressure here and you'd end up with high pressure here, and the pressure would increase proportional to the distance in both cases, and that explains why electrons and protons move. And then you're just saying for gravity, okay, that you're taking all of this equation of all of this deflection, and if you could just recognize that if I take all of these blue and white objects and I randomize their orientation, that is their polarity, that the fact that they're diverting force gets lost because I have them in so many different orientations, and so they end up diverting the force. You could sort of understand if I had a bunch of little magnets, I have these things lined up with each other, and their orientation to each other is all randomized, mixed, that I'm going to end up, okay, with the same circumstance. All of these diversions are all going to add up to nothing. Okay, they're going to add back up to a random force again. So if I haven't got any polarity in here, I haven't got any magnets lined up, all right, if I have them all mixed up all over the place in all directions, then all the right turns are going to be negated as an effect. And so now all I'm going to have is the mass of the charges, and the only way they can change the force, right? The force is coming in equal amounts of both kinds, and the only way they can affect anything is just by moving. If they move, they've absorbed a force while they're moving, and they can change what comes out and how much force gets through them by moving as the force affects them. And that's gravity. But gravity's really charge. It's charge diluted by mixing it. Once you mix the charges, you're back to just a force. Red and white, blue and white don't matter anymore. So that's all that the real force, the real first force, is charge. All right. Again, I can only offer you, the opportunity to be reasonable and rational. If you don't want to take it, then frankly, you're really a jerk. You don't want to be reasonable? Well, you really don't, though, right? I mean, these people would only be this aggressive, if they're having a real panic that they just don't want a deterministic mechanical universe. They don't want this simple answer. They want a wooey answer because they're still looking for a God they can like. And that's all that's going on here, frankly. So, until the next time, I shall endeavor to persevere.